Hello everyone, this is another video from Easy Electric series, and today we want to design a 4-bit asynchronous up-down counter. So what it means actually you want to have a counter which able to have one input. We call that A. So with that input you are able to telling your counter you want to actually count up or down. So, for example, if you consider we have one extra input, I call that input A. So whenever this is A is a 0, it means the counter should be count up. Usually we use these bar, which means these the 0. If you put the 0, that's actually up counter. If that's 1, it's actually is a down counter. So whenever the A is 1, you need to actually count that down. So let's see how we could design these up-down counter. So if we check our previous video, in two previous video, we talk about the 4-bit asynchronous up counter and also 4-bit asynchronous down counter. So if you check their structure, so for example, this is what we had or what we designed as a down counter. So we use actually 4 T flip-flop, and this is how we design that. So and this one is the up counter. Again, we use 4 T flip-flop and we design the up counter. So right now, somehow we want to combine these two design and actually get up-down counter. So let's actually take a closer look to both of these design and see what's their similarity and difference. So the first thing is that all of them use actually 4 T flip-flop. The down actually use the rising edge T flip-flop, but actually the up counter use actually falling edge T flip-flop. So this is actually the first difference. So here this flip-flop is the rising edge sensitive and this is falling edge. So what is the next? The next is this initial circuit that we have for up counter. The initial circuit is connected to the all clear pins, but in the preset, in a down counter, so the clear connected to the 1 and preset actually pins connect to each other, and they actually make the initial circuits, which is whenever you active this initial circuit, it's actually load 40 in your counter for down counter, and for up counter, whenever you active this initial input, it's actually load 15 in your counter. Then you start to actually count down. So again, in the up counter, so initial load 40, and in actually down counter, it actually should be load 15. You start to count from 15 to 0. So let's see how we could actually somehow combine these two and design our 4-bit up-down counter. So the first thing is, so if you actually take a look for the two previous design, so definitely we use actually 4 T flip-flop. So definitely here we actually use again 4 T flip-flop as a core of our design. So I'm actually putting here, so yeah, maybe here is better. So I put the first one, which is T flip-flop. So then you need a second one. Again, it's T flip-flop. The third one, again, it is T flip-flop, and the last one is another T flip-flop. Okay. So as you already know, each T flip-flop has 2 input. One is the T, what we usually call this 1T, which is your T input, and the next one is your clock, right? So this is your actually clock that you have here. So now the first question is, so for up counter, we actually use the T flip-flop, which is sensitive to the falling age clock. So here for down counter, you use actually rising age T flip-flop. So the question here is, what about the up-down? It should be the rising age or falling age. So let I just get rid of this. We actually, right. So the answer is, okay, so let's do this. Let's use actually the falling age clock. So this is our, usually use the CK so as a clock. So I'm using the all rising age, and I explain why. So based off up and down, it should be rising and falling. I actually put the rising age, but you already know with just putting a knot in your pass on your clock, you could actually change that to the falling age. So for that reason, here I use one mux, which is to actually draw that a little to, yep, let's actually erase this and use the same color or different color. Okay, so here I'm going to do this. I'm actually putting one mux or multiplexer, which I call that mux 2 by 1. I connect the output here, and you already know we have one video we explain how multiplexer works. So here 2 1 means you have 2 input, 1 output, and you have 1 address bar, which is we give these A. These A is the same, these A, which is tell you we should be up or down. So if A is 0, so you have actually 2 inputs, right? So the 1 is 0, here is 0, this is actually, yeah, to put here, this is input 0, this is input 1, okay? So whenever A is 0, it should be actually, a counter should be actually up counter whenever A is 0. So that means it should be up counter. So back here, whenever it is up counter, you should have actually the falling age. So that means this is not right. You should actually take a knot of the clock pulse. So if this is the clock pulse input, actually connect directly this to this and then take one knot and connect that to here. So let's see if it works or not. Whenever A is 0, you actually connect these input, the first input 0 to here. That means you add one knot. So that means this T flip-flop is actually falling age whenever you have actually up counter. Is it right? Yeah, for up it is falling age. But whenever it is down, it should be actually the falling, sorry, it should be rising age. So see here. Whenever it is actually 1, it's connect this. That means these clock directly connect to these clock pulse, which is actually already rising age. So that means whenever A is 0, somehow all these T flip-flop that you use, whenever A is 0, they are falling age because of these knot. So whenever A is 1, all of these T flip-flop is actually rising age because there is nothing in here. So you directly connect this clock to here, which is actually make that actually rising age. So you do the same thing for all these 4. So same explanation. So I just put one actually the mux here. So this is mux 2 by 1. I connect the output here, so you already know what should be the input, right? So let's actually put the mux here, then we talk about the inputs, okay? So I do the same thing here. So you have here the mux 2 by 1. Same thing here for this, which is max 2 by 1. So one thing I'm sure, which is this address bar should be actually A, which is depending on A is 0 and 1, it should be actually give a different actually clock to these pins that we have. So again, let's to check with the pin 0, okay, so this one. So whenever A is 0, it should be up counter. Let us see if it's up counter what we should connect to these pins that we have. So this is actually the up counter. So whenever this is up counter, you should actually connect this Q0, which is the output of the first T flip-flop to your clock. Okay, so let's do that. So the Q0 should be connected to this, Q1 connected to this, Q2 connected to this. So I'm going to do that. So this is my, I just change the color again. So this is my Q0. This is my Q1. This is my Q2. This is my Q3. So again, whenever this is 0, the first this actually pin connected here should be up. So if that's up, it should be the knot of the Q connected to here, right? So for that reason, I actually connect the Q0 here. So see, I actually connect Q0. So here you have the Q0, and you already know that we have two output for T flip-flop. One is the Q0, the next one is Q0 prime, right? So if you check again, the A is 0, it should be connect these pins, it should be up, and what you have here, you should have like somehow have these not, right? So that means whatever you connect here is Q0 not, because you use actually just rising A. You need to have these not that you see. For that reason, I'm not connecting the Q, I'm connecting to Q0 not to this pin 0, something like this, okay? So Q0 not, right? So whenever it is Q is 1, it should be down counter. So what we connect to these pins whenever we have down counter, just check the design. So you actually directly connect the output of the first T flip-flop. So that means I'm connecting this Q0 here. So I actually connect Q0 and use a jumper and put that here, okay? So you could actually double check that. So whenever A is 0, the mux, this is input 0, this is input 1 of the mux. Whenever A is 0, so the output, this output is this, which is Q actually prime or Q0 not. So that means you are in, whenever A is 0, you are in the up counter. So whenever you are in the up counter, what should be connected? Q0 not, right? So that's the reason you have this Q0 not here. So whenever this is 1, it is actually down counter. In down counter, which is this, you actually directly connect to here, which is the Q0. So that's the reason I actually put these exactly here, okay? So with the same argument, we could actually complete these two. If you again do the same thing and check the both of them for the third actually T flip-flop. So again, you connect Q1 prim to these 0 pins here. So this is pin 0, and Q1 actually use the jumper and connect to this one, okay? So the same argument here. So for this one, you do the same thing. So you actually connect Q prim directly to pin 0, and this one should be go to the second input, which is 1. Okay, so if you check, you could actually check that again. So whenever A is 0, so suppose A is 0, so that means you connect all these 0 pins to here, right? 0 to here, these pins to here. Okay, so that means it is up counter. So that means here you have clock not also, which is right, because for up you use actually the falling edge. That's the reason you have these not here, right? So same thing here. So here you connect actually Q0 not, somehow you have Q0 and add the not here is the same thing, right? So see, you have here Q0 not. So the same for all others. So Q1 not and Q2 not because of this circle that you have. So see, for all of them you have Q1 not and Q2 not and nothing for the last one. Okay. So whenever it is 1, actually you have exactly the down counter, so that means you have exactly these actually circuits. So depending on A is 0 and 1, exactly we switch between this or this circuit by using just one multiplexer. So how about these pins? So if you check the both circuits, so up and down for all of them is 1. So that means you don't need any things for that pins. You just actually add a 1 similar with the up and down design. So that's the reason here you have 1, you have 1, you have 1. Okay. So far we are good. So as you already know, each T flip-flop has one, actually the clear pin and also preset pin, PRS, right? So whenever it is actually the down counter, so see, whenever you have this down counter, so you need one initial input. What it means, that means before you start to count, you should somehow active this. It should be load 15 on your counter, then you start to count 15 to down. So for this, we in the down counter, we actually connect all the presets and say, okay, this should be our initial circuit. So the same thing for up counter. So for up counter, initial circuit should be connect for all clear. You just active that before your counter starts. So if you active this, it's actually initialize 4-0 inside your counter, then you're able to start to count from 0, go up to the 15, right? But here the question is, what should be initial circuit? So that's actually a big question. So somehow whenever A is 0, it should be, whenever A is 0 is actually is up counter, so that means should be this. So whenever A is 1, should be this. So let's see how we could design that. So it is actually somehow a combinational circuit design problem. So I actually designed the initial circuit in this way. I say, okay, I want to design a combinational circuit. So first question is how many inputs I have. So the answer is I have 2 input. One is the A, the next one is initial circuit or INT bar, which I need for up and down counter. So these are the 2 input I have. So the next question is how many output I have. So I have 4 clear or reset pins for the each flip-flop. I have 4 preset, right? So actually list them. So clear, I have a 0 to 3. It is 4. I just write 0 to 3. Maybe that's better to put this 0 to 3, which is 4 output. And the same thing I have for preset, PRS 0 to 3. Okay, so totally is 8. I just want to save some space. I just put clear 0 to 3, preset 0 to 3 though. So technically each of them is 4 actually output. Okay, so I have two inputs, so I'm in the base 2. So if you have two inputs, how many different cases is possible? So A could be 0 1, initial could be 0 1. So the answer is you could have 4 different cases. Okay, I just list that 4 different cases. 0 1 is 0 1. So if you forget how you could design the combinational circuit, please watch our video. We have two videos for how you could design combinational circuits. So if you forget how you could design that, you need to actually watch that two videos which explain how you could design any combinational circuit. Here we want to design combinational circuit with two inputs and 8 outputs. So we actually put the all possible inputs that we could have, so which is 0 0 0 1 0 1 and 1 1, and we want to see in each case what we should have. So I just separate these cases. So let's to check this. So whenever A is 0, based on our design, whenever A is 0, we want to have up counter. C0 is up and A is 1. So A is 0, so that means I want to have up counter and I active the initial circuit. What should be happen? So whenever you are in the up counter and you active the initial circuit, so you are going to count up. So that means it should be load for 0, right? So that means all clear 0 to 3 should be 0 and all preset should be actually not active, which is deactive by 1. Okay, check the next one. A is 0. This is up counter, and you actually don't active the initial, right? So you active the initial circuit with 0. 1 is it's not active. So that means the A is 0, initial is not active. So the counter should be do its normal work. We don't need clear and preset. So that means all of them should be deactive, which is deactive by 1. Okay. So check the next one. The A is 1, so that means we have down counter and you active the initial circuit. Whenever you are actually in down counter and you active the initial circuit, it should be load 15. How you could load 15? With actually putting 0 in for these preset pins that you have here, right? So that means this should be actually 0. How about the clear? You don't need clear in down counter. They should be actually deactive, which is deactive by 1. Check the next. A is 1. You have down counter. The initial circuit is not active. The counter should be do its own job. So that means you don't need actually preset and set and reset. So that means the both of them should be 1. Okay, so I complete the truth table of the circuit that I want to design. So right now I just need to find these actually the clear and preset base of my input. Okay, I just write one of them. So C, for example, CLR 0 to 3 bar, which is that means all of them is the same value, right? So equal to what? You actually help me. So if you consider that as a max term, so here it is just equal to the max term 0, right? So max term 0 is what is A plus whatever you have here, which is the INT bar. Okay. So again, if you forget how we could actually get this, please check that two video, the combinational circuit design, and then you could able to understand what I'm doing here. So the same thing for preset. So you check the preset. So here is 0. The preset is just the max term. What's the number of the max term? Here is max term 2, right? So because there is just one max term, you don't need to actually use the K map to get the simplest form, right? Because here for both of them you have just one max term. So there is no need for actually make that simple. This is the simplest form. So PRS bar again 0 to 3 equal to actually check the same, the A is 1, so you should have A prime plus actually int bar, okay? So let us see implement these, okay? So that means here I actually make both of them. So I actually make one initial circuit. So this is, suppose this is your input, int input, okay? So you need actually two OR gate, right? This is one OR gate. So this is actually the second OR gate, okay? So one actually is int bar, so this should be goes for all of them. So the next should be actually input should be A, right? So this is A. So A plus initial should be connect to the all clear, right? See what I'm doing here? I connect clear 0, 1, 2, 3, which is the all clear that you have, and connect that to the 8 plus int bar, right? I connect this to this, okay? That's it. So how about the preset should be A prime. So see, I use one not, then again I have A, so you have A not, int bar. So the OR then it should be connect to either the OR, the preset that you have. So see again what I'm doing here. I connect preset 0 equal to preset 1 equal to preset 2 equal to preset 3, and that should be connect to this one, which is I jump over there and I connect this. So that means preset 0 to 3, which is connected, is equal to A prime plus int bar. So because I don't want to actually make very complex design, so that's the reason I separate these A. But technically all these A should be connected to each other, and just you have one input as A for up down counter. So initially is actually is 1, so you have two actually extra inputs. Whenever the A is 0, these counter should be actually a count up. Whenever this is 1, it should be actually count down, okay? So how it's work, for example, if you want to, it should be the up counter, you give A 0, then you active this initial, it should be able to actually load for a 0. So then it will start to count 0 to 15 and again back to the 0. So if A is 1, it should be go actually down. So you active initial, it's load 15, then after that it's count down from 15 to 0 again back to the 15. Even if you could actually check this, so see, whenever A is 0, so that means it is up counter, right? I just checked the up counter, A is 0. So let's see what we have for clear 0 to 3 pins. So this is 0 plus, so again int, if you active the int, give the 0, so you have 0 or 0, that means 0. So that means you give the 0 for all clear pins, which is load for 0, right? That's right. How about the preset? You have a 0, you have 1 plus anything, it should be 1, so that means you deactivate the preset. That's right. You could actually check the same thing for the actually the down counter, okay? So what I have here, I'm going to simulate our design in the Multisim and make sure our design work. So what I have here is exactly the same circuit that we designed, okay? So you see this circuit, I exactly implement that here. So as you could see, you have T flip-flop, but I just use the JK, just actually connect J to K. If you connect J to K, so that's actually you made the T flip-flop, okay? So these are that 2x1 mux, which is U4, 6, and 7. So which is the same thing that I already explained, okay? So here, this is your clock. So which is I give, if you check the clock, it is 250 megahertz. So you could change that if you want to fast, slower, or actually faster. You could actually change the frequency of your clock. So see here we have, this is exactly the same circuit. So this is first input, which is initial, and this is up down. So see how it's worked. So if you put this switch here down, which is connected to 0, this connected to 1. So that means right now it is connected to 0. So that means whenever this is here, it should be count actually up, right? So then I need to initialize, right? So here you just initialize that. I put that here to, yeah, first I need to actually start to simulate. So see, this is actually here, which is the 0. It should be go up counter, and I initialize for a short time. It's load for 0, and now it's actually back to the 1. It should be start to count from 0, then 1, then should be actually 2, then should be 3, right? 2, 1. So this should be 4, this should be on, this should be actually 0, right? So this is binary. 4, then should be 5, this and this should be on. There should be 6, so this should be 6, then should be 7, it should be on 2, then it should be 8, just this should be on, and all other should be 0, then it should be 9, this should be on 2, so then should be 10, just these two should be on at 10, so right now. So then 10, 11, you should have this on 2, then you should have 12, these two should be on, which is on, then 13, you should have this on, then you should be have 14, which is these actually 3 should be on, and the last one is 15, all of them on, and back to the 0, right? 15 to the 0, so see, back to the 0. So again, start to go 1 and 2 again, okay? So that means right now the up counter works, and the fun part is this. Right now I won't actually make that actually down counter. I need to change to the here, which is right now I'm telling, okay, this is 1, so it should be actually right now actually down counter. So again, you initialize first. If I put the initialize, see, because this is actually down counter, it's load 15, right? So now deactive initialize input, it should be go 15 to the 14. This is 14. So then it should be 13. So this is 13. So then it should be go to the 12. So this is 12. Then go to the 11. So this is 11. So then should be go to the 10. So this is 10. Then should be 9. So that's right. So then should be 8, just should be on. So then 7, these 3 should be on. And then you have 6, just these 2. Then you have 5, which is this and this. Then you should have a 4, just this. Then you should have a 3, just these 2. So see, you are counting down. So then 3, 2, then 2, then 1. This is 1, then 0. And then you need to back to the 15, right? So wait to 15. Yep, maybe back to the 15. So that means it works, okay? So I actually stop this and see what I did as a next simulation. I add one binary to 7-segment code converter, which I want to see the real number, not here. I just see the binary. Somehow you need to keep in your mind, okay, this is 15, how it's worked. So what I did here, it's exactly the same circuit that we already simulate that. Just here I add one. What you see in this part in the right side is binary to 7-segment code converter, which we have a video for that. If you check the channel, I explained the binary to 7-segment code converter in one of our videos. So also we simulate that. So this is the same thing. So that means here I just want to see the counting up and down. I just want to check with this binary. So let's do check that again first. Let's do push the button, we simulate that. So right now, see, this is the 0. I put that here to 0, so I want to start with the up counter, okay? So this is on 0, it should be count up. This is initialize. I initialize that immediately. You see this 0, right? So then you deactive initialize, it start to count up, right? So see, it goes to the 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and again back 0. It's going to continue, okay? So now I put these to the down counter. So see, this is here is should be down counter and initialize that. So that means it's immediately load the 15 because you want to actually down counter start to 15. So the initial is active, it is 15. Then if you actually deactive the initial, it start to counting down 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 0, and 15. Again, back to the 15, okay? So that means you could actually control with this switch for up and down, initialize that, and this should be your up-down counter. So I hope you like this video. Please don't forget to subscribe to channel and let us to upload more videos. Thank you so much for watching.